Today we are going to discuss the topic heat equation. Heat equation and its solution by using the Fourier series method. Solution by Fourier series. Okay, Fourier series solution of heat equation. This is too bright. I think this is okay. Heat equation solution by Fourier series. Okay, so what is the heat equation? The heat equation is given by this differential equation. Del U by del T is equal to C square Laplacian of U. And what is C square? C square equal to capital K divided by sigma times rho. Okay, so this is the heat equation. The heat equation, this gives the temperature gives the temperature U as x, y, z, t in Cartesian coordinates in a body of homogeneous material. So this is the heat equation, and it gives the temperature in a body of homogeneous material. Okay, here C square is the thermal diffusivity. Is the thermal diffusivity. PIFUSIVITY is thermal diffusivity. Capital K is the thermal conductivity. And this sigma is the specific heat. Sigma, the specific heat. Okay, and this rho is the density of the material, and rho, the density. Rho is the density of the material of the body. Okay, so this is the heat equation, and if you compare this heat equation with the wave equation which we discussed in our last class, you'll find that the difference is mainly here. In the wave equation, we have second order partial derivative of U with respect to time. However, in the heat equation, we have only first order partial derivative of U with respect to time. Okay, and this equation is also called the diffusion equation. It is also called the diffusion equation. Okay. Okay, now as an important application of this heat equation, let us first consider the temperature in a long thin metal bar or wire of constant cross section and homogeneous material. And for simplicity, we assume that this metal bar is oriented along the x-axis and is perfectly insulated laterally, so that it flows only in the x direction. Okay, so let me draw the diagram here. I have a metal bar, long thin metal bar. Okay, and this is the x-axis. This is the x-axis. The long thin metal bar is lying on the x-axis. So the long thin metal bar is lying on the x-axis. The ends are at x equal to 0 and x equal to L. So this is the long thin metal bar. Long and thin metal bar. Okay, this is the x-axis. The metal bar is lying along the x-axis. The ends of the metal bar are at x equal to 0 and x equal to L. So the metal bar is of length capital L. Then let us study the temperature distribution in this metal bar. Okay, so here the temperature in this particular case, here the temperature U, it depends only on x and time t. Okay, and the heat equation becomes the one-dimensional heat equation. The one-dimensional heat equation, which is given by del U by del T is equal to C square del 2U by del X square. This is the Laplacian in one dimensions. Okay. So we write this as equation number 1. We call this equation number 1. So this is the heat equation in three dimensions. So in one dimension, this Laplacian reduces to second order partial derivative with respect to only x. Okay. So this is slightly different from the wave equation which we discussed earlier. In wave equation, this is second order partial derivative with respect to t. Okay, but here we have first order partial derivative with respect to t. Okay, and because of this difference, the solution of the heat equation will behave quite differently from those of the wave equation. Okay, so let us solve this equation 1 for some important types of boundary conditions and initial conditions. So let us begin with the case where the ends x equal to 0 and the ends at x equal to 0 and the ends at x equal to L of the bar are kept at a temperature 0. So let us start with a simple boundary condition in which this end of the bar is kept at 0 temperature and the other end of the bar is also kept at 0 temperature. Okay, so the boundary conditions are the boundary conditions are U at x equal to 0 at any time, this is 0, and U at x equal to L at any time is also 0 for all t. This is 0 for all times, for all time t. Okay, this we call equation number 2. Fine. So we are going to solve this differential equation subject to this boundary condition. And furthermore, we need to add the initial conditions. Okay, so let me write it on a new sheet of paper. So we have the boundary conditions. Now let us look at the initial conditions. Say and what is the initial condition give? The initial condition gives the temperature distribution in the bar at time t equal to 0. So the initial temperature in the bar, the initial temperature in the bar at time t equal to 0. At time t equal to 0 is given by some function. Let us call it f of x. Okay, because at time t equal to 0, this is the temperature distribution in the bar. So that we have the initial condition, so we have the initial condition. And what is the initial condition? The initial condition is that u of x at time t equal to 0, this is equal to f of x. And here f of x is some function which is given to us. And f of x represents the temperature distribution along the bar. Okay. And from the boundary conditions, and what are the boundary conditions? The boundary conditions are that at x equal to 0, the temperature should be 0. At x equal to L, the temperature should also be 0. So f of x should have the following property. Okay, here f of x must have the following properties. That is, the value of f at x equal to 0, it should be 0 because the ends of the bar are kept at 0 temperature, and the other end, so the first end is kept at 0 temperature, the other end at x equal to L is also kept at 0 temperature. This was the boundary condition. Okay, because of the boundary condition, equation 2. Okay, so this is the temperature distribution across the bar, and this f at x equal to 0 should be 0, and f at x equal to L should be 0 because this was the condition imposed by the boundary condition. Okay, now we shall determine a solution u of equation number 1, that is the wave equation. So what are we going to do now? So now we are going to determine a solution of this of this diffusion equation or heat equation, satisfying the boundary conditions given by equation number 2 and the initial condition given by equation number 3. Here we have only one initial condition, and this is enough. Unlike the case where we had 2 initial conditions for the wave equation. And technically our method of solution will be parallel to that of the wave equation which we discussed earlier. We shall use a separation of variables method followed by the use of Fourier series. So a step-by-step comparison would be very helpful in these 2 cases. Okay, so let us start with step 1. Step number 1. Okay, and what did we obtain in step number 1 in the case of wave functions? In the case of wave equations, we obtained 2 ordinary differential equations from the wave equation by using the separation of variables. Okay, so here also we are going to obtain 2 ordinary differential equations from a single heat equation by using the separation of variables. Okay, so as the first step, we set u t is equal to a product of 2 functions, f of x and g of t. Okay, so let the temperature be given by f of x and g of t, where f of x is a function of only x and g of t is a function of only t. Now let us substitute this in equation number 1. Okay. Substituting this in equation number 1, And what is equation number one? Equation number one is the heat equation. We get, so let me show you the heat equation again. So here is the heat equation. So if you substitute U equal to Fx Gx, so this is partial derivative with respect to time. Okay. And this is partial derivative with respect to x. So if you take the partial derivative with respect to time, so what will we get? So if first we take the partial derivative with respect to time, then we shall treat f of x as a constant. So it will we shall get f, then partial derivative of t, g with respect to time, f dg by dt. This is what we get from the left hand side. This is equal to c square. Now this is second order partial derivative with respect to x. So that means we can treat g as a constant, and then d2f by dx square. Okay. So this is what we obtain, right? Now to separate the variables, what do we do? Now we divide both sides by c square. So let me write it here, dividing both sides, dividing by c square fg we get. So let me remove this now. Dividing by c square fg on both sides, what do we get? We get, so this will become 1 by c square g dg by dt. This is equal to 1 by f d2f by dx square. Okay, this we shall call equation number 4. Fine, so far so good. Now if we look at the left hand side, we see that the left hand side depends only upon t, the time t, while the right hand side depends only upon the variable x. So let me write it down here. The left side depends only on t, and the right side only on x. Okay. So that means both sides must be equal to a constant. So that both sides must equal a constant. Let us call it k, constant k. And last time in the case of wave equation, we see that for k equal to 0, the only solution satisfying is the trivial solution u equal to 0. And also for the case k is greater than 0, we show that the only solution possible is u equal to 0. But that is not the solution which we want. So that means the only possible value of k is a negative number. Okay, so for let me write it here. We may show that for k equal to 0 or k a positive number, the only solution u equal to fg satisfying the boundary conditions, equation 2, is the trivial solution u equal to 0. Okay, but this is not the solution we want. So what should we take? We should take k as a negative number. So let me write it on a new sheet of paper. So for negative k, we can write it as minus some p square, where p is any number which can be positive or negative. So when we take the square of a number, the answer is either 0 or positive. But since we have ignored the case k equal to 0, that means this p is not 0 and p can be any number. And if we take the square of any number which is not 0, the answer is always a positive number. And now if you multiply it by -1, the answer is always a negative number. Okay, so this means k is a negative number. Then we have there is no comma here. We have from equation number 4. Equation number 4, that is this equation. Okay, equation number 4 is this equation. So both sides should be equal to a constant k, and k is equal to minus p square. Okay, so what do we have from equation number 4? From equation number 4, we have 1 by c square g dg by dt is equal to 1 by f d2f by dx square. This is equal to minus p square. Okay, from this we can obtain two ordinary differential equations. So multiplying so let me remove this sheet now. Multiplying by the denominator, denominators gives immediately two ordinary differential equations, which we write in short as ODEs, ordinary differential equations. And what are the ordinary differential equations? If we look at this first, what do we get? We get d2f by dx square, and if I multiply by f on both sides, I should get d2f by dx square is equal to minus p square f. And now if I bring p square f towards the left, what do we get? We get d2f by dx square plus p square f. This is equal to 0. Okay, so this we call equation number 5. Okay, this is fine. Okay, next. Now from this, if we multiply both sides by c square g, I should get dg by dt equal to minus p square c square g. And if I bring p minus p square c square g towards the left, what should I get? I should get another differential equation, dg by dt. This minus, if I bring it towards the left, it will become plus. So c square p square g is equal to 0. This we call equation number 6. Okay, fine. So this is the end of step number 1. So what have we done in step number 1? In step number 1, we started with a partial differential equation, and by using the method of separation of variables, we have obtained two ordinary differential equations given by equations 5 and 6. Now, what is step 2? Now, step 2, we are going to apply the boundary conditions. Okay, so we are going to find the solutions of these two equations which satisfy the boundary conditions. So number 2 is satisfying the boundary conditions. Boundary conditions given by equation number 2. Okay, so what are the boundary conditions? The boundary conditions are given by this. At x equal to 0, the temperature is 0. At x equal to capital L, the temperature is 0 for all values of t. Okay. Okay. So first we solve equation number 5. A general solution of equation 5 is given by f of x. This is equal to a times cos px plus b times sin px. Solution of this equation number 5 is very simple. This we learned in our first semester. This is a simple differential equation. This is second order linear differential equation, and the solution is given by this. We call it equation number 7. Okay. One moment. Okay. Now let us apply the boundary condition here. So from the boundary conditions given by equation number 2, it follows that u of when x is equal to 0 for any value of t, this should be equal to f of 0 for any value of t. This should be 0. And u L for any value of t, this is equal to f L G T. This should also be equal to 0. Okay. But if we take g equal to 0, that means the solution u equal to 0 for all values of t. So since g equal to 0 would give us u equal to 0, we require that f of 0 should be equal to 0 and f of L should be equal to 0. So let me repeat this part. Here we have a product of two functions, f of 0 gt and f of L gt. The product of two functions is 0. That means either one of the two functions is 0. But g of t cannot be 0, because if g of t is 0, then u will always be 0. That means the temperature throughout the bar is 0. The temperature distribution throughout the bar is 0, but that is not what we want. We want non-zero solutions of u. So we cannot take g equal to 0. That means the only other possibility is that f of 0 should be 0 and f of L should be 0. Okay. We had a similar argument for the case of wave equation also. Okay. Now, if I put f of 0 equal to 0 in equation number 7, what do I get? If I put f of 0 equal to 0 in equation 7, f of 0 equal to 0, putting f of 0 equal to 0 in equation 7, what do we get? We get 0 equal to a. When you put x equal to 0, f of 0 means when you put x equal to 0, the function f should be 0. So the left hand side is 0 when x is equal to 0. Now if you put x equal to 0 here, this becomes cos of 0. And what is cos of 0? Cos of 0 is 1. So we have a multiplied by 1, and that is a. Next, sine of 0. And what is sine of 0? Sine of 0 is 0. So 0 multiplying on b is 0. That means that the second term does not appear here. So if we put f of 0 equal to 0, we get the condition that a is equal to 0. Okay. So what does it give us? Then it gives us that, let me write it on a new sheet of paper. So if I use the first boundary condition, f of 0 equal to 0, it gives me a should be 0. That means equation number 7 should reduce to, so that means this equation, therefore f of x, in f of x, a is 0, therefore the new form of f of x should be b sine bx. Okay, because a is 0. A is 0 means this term will vanish. Now, if I use the second boundary condition, that is when x is equal to L, f should be 0. Okay, so putting f of L equal to 0, or from, we can write from f of L equal to 0, we have, if I put f of x equal to L here, I should get 0 equal to B sine PL. Okay, B sine PL. And B cannot be 0, because if B is 0, then this solution will always be 0. So what is the only possibility left? The only possibility left is sine PL is equal to 0. Since B is not equal to 0, we have sine PL is equal to 0. And this implies P is equal to n pi by L, where n is 1, 2, 3, and so on. Okay, n is not equal to 0. You should remember here that n is not equal to 0, because if n is equal to 0, then that means P is equal to 0. And if P is equal to 0, the function is 0. Oh, and that reduces to the trivial solution u equal to 0. So that means n can take only non-zero integer integral values. N can also take negative values, but that does not give us new solutions. Okay, so it is only sufficient. It is sufficient to consider only positive integral values of n. Okay, and for simplicity, setting b equal to 1, we thus obtain the following solution of equation number 5. And what is equation number 5? Equation number 5 is this equation. Okay, equation number 5, satisfying the boundary condition. Satisfying the boundary condition given by equation 2. Equation 2 is f and x. This is equal to sine n pi by L. We have fx equal to sine px, and for simplicity we take b equal to 1, so sine px. And what is p? P is n pi by L, so we have sine n pi by L x. So for different values of n, I get different values of p, so I can add the subscript n here. Okay, so for different values of n, I'll get different values of functions, and all these functions, they satisfy equation number 5. This. Okay, so equation number 5 has infinite number of solutions for different values of n. Fine. And so far, this solution is similar to what we obtained in the case of wave equations. Then where does the difference start? The difference starts from equation number 6. In wave equation, this equation number 6, it was a second order differential equation in G, but now we have only first order differential equation in G. So that is where the difference starts. So let me pause the recording here.